All right. Well, I hope you enjoyed the little. Hello. Yep, it is running. I couldn't tell if it was on or not. Okay, I hope you enjoyed the little experiments. Now we're going to read force and we'll answer our questions. And I, of course, will. This is a handout, and I will make sure you get it. Okay, we're going to stop talking now. We just had a whole talk about respect. And notice they're still talking. Okay? We had a whole little speech about respecting others, and yet they're talking as I'm trying to address you. Wow. Wow. See, I want to make. I'm including you in what was going on in class at all times. All right. What is force? Okay, we talked about this the other day. In physics, force is a push or a pull on an object. A force can cause an object to accelerate, slow down, remain in place, or change shape. Remember we talked about the push and a pull, opening and closing that door, or open it from the inside, open it from the outside. There's a push and a pull, okay? Causing it to accelerate, slow down, remain in place, or even change shape. Think about the ball. We talked about the soccer ball the other day. When you kicked it, somebody would stop it. It would change directions, the whole bit, okay? But it won't do any of that without force being applied to it, okay? You take a soccer ball and lay it in the middle of a soccer field, and barring an earthquake or a strong wind or something, if no one walks up, picks it up, kicks it or anything, that ball will just lay there. It's not going to go anywhere unless there is a force applied to it, okay? The unit of measure for force is a Newton. We talked about that. Named after Sir Isaac Newton. It's abbreviated as a capital N. 1 Newton is the force needed to accelerate 1 gram of mass by 1 centimeter per second squared. Other unit of force includes die and pound force. Okay. Force, mass, and acceleration. Force can be figured out if you know the mass and the acceleration of an object, okay? The equation comes from Newton's second law of motion, which is the law of acceleration, also known as the law of acceleration. So it's force equals mass times acceleration, okay? That's all it is. Force times equals mass times acceleration, okay? Forces and vectors, we're not going to get into vectors a whole lot. They can get rather complicated. When you get into physics in high school, Mr. Feeney, Ms. Founds, I'm sure you'll get into vectors a little bit more math and things is involved in these. Force not only has a magnitude, which is what we get in Newton's when we use the equation above, but it also has direction, okay? So force is a vector simply because it has magnitude and direction, okay? Let's say the wind blows 40 miles an hour east, okay? That's magnitude and direction, okay? Yes?
Miss Founds has a newt named Newton after Sir Isaac Newton.
Okay. Vectors are shown, she does. Vectors are shown by an arrow that indicates the direction of the force and the number that indicates the magnitude. Okay? See the picture to the right to see how, and it's actually up top. But you see how we use arrows to show the force, which way it is going. Okay? And of course, the longer the arrow, the more force being applied, things of that nature. Okay? All right. Force is in equilibrium. Okay. Now, sometimes there can be many forces acting on an object, but the object remains still. In this case, the forces are equilibrium. Okay? The sum of the force is a net force is 0. Remember we talked about the picture in the book had the big box. and you had people of pretty much the same size, one on one side, one on the other, both of them applying the exact same force
Oh, yeah.
in two different directions, okay? They were going against each other. So the box is not going to move. When we did the little rope thing up here, and we were pulling at about the same force, neither one of us was moving, okay? Neither one of us was moving, because we had it was equal. The forces was equal, okay? So the net force was 0. Yes?
If there was a force acting on an object, but that object was so heavy, would it still move even though really, really slow?
You got to apply enough, you got to apply enough force. I can go out right now with my truck being in park. I can go out and get behind it and just push like crazy. And that truck's not going to go anywhere, right?
I mean, it
So
might.
no matter how much force I apply, I'm not going to move that truck. So the net is going to be 0, even though I'm applying quite a bit of force to it. I'm not moving anything.
It might.
So no, just because you apply force to something doesn't mean it's going to move. You got something that weighs 500 pounds and you apply 100 pounds of force, it's not going anywhere.
You can try that on my face.
Okay, not going to go anywhere. But that's a good question. Okay.
It was just.
The picture below shows an object sitting on a desk. Okay, the object isn't moving, and this is because the force of gravity is pulling that object down is equal to the opposite and opposite to the force of the table pushing up. Okay, the net force is 0, and the forces are equal. Okay, we're talking about Macy's. What do you call that thing? Binder, yeah. My mind just went blank. Or Rihanna's water bottle, whatever, sitting there. Gravity is pulling that down. Okay, but you also have the force of the desk pushing up on it.
So yeah, that's.
But because it's equal, the water bottle is not going to go anywhere unless Rihanna applies more force to it and moves it herself. Okay, it'll just sit there. Okay, all right. When multiple forces are acted on an object, the force is the sum of the vector of the individual forces. And we're not going to get into that. We talked a little bit about getting into vectors. It's some pretty complex math. So we're not going to get into that here. But we did talk about if two sides are pulling, and one side is pulling with a force of 2 newtons in the left, and the other side is pulling with a force of 3 newtons to the right, then the result force is 1 newton in the right direction. So the other day when Evie and I was tugging on the rope, okay, if I'm over here pulling with 2 newtons and Evie is over here pulling with 3, she's going to move me, okay? She's going to move me, and the net force is going to be 1 because she's pulling with 3, I'm pulling with 2. 3 minus 2 is 1, so you got 1 newton, okay? Now, you got different types of forces, okay? We have friction. Friction is a force caused when one object rubs against another, and it works in the opposite direction of the main force. So, this carpet would create, if I was trying to slide something really heavy across this carpet, it very well might create friction, although it's not shag, it's pretty thin. It would make it hard because as I was pushing something towards the door, the friction would be working against me, okay? Because it's going to try to keep me from pushing it that way. So friction works in the opposite direction of where you're trying to go. Yes?
Is there also friction when I place this pencil on the table? Like an example of the objects?
Only if you're trying to move it one way or the other. And even then, with the desktop being slick, you're not going to get a lot of friction. Now, if you was to take that pencil and try to pull it across a really coarse piece of sandpaper,
There'd be friction.
there would be friction there.
There'd be plastic shavings everywhere.
If you try to pull it across a piece of glass, a really slick piece of glass, very little friction, if any, at that point in time. Because it depends on the coarseness of what you're trying to push against.
Okay.
Okay? Gravity is a force caused by a large body, such as the Earth. Now, you're going to want to remember this, okay? Or at least know where to find it. Gravity pulls objects towards the Earth with an acceleration of g, okay? Which equals 9.8 meters per second squared. So when you have a math problem, and you will eventually, where you have to plug in gravity, gravity is 9.8. 9.8, okay?
Why do you always have to remember that stuff? Like pi is 3.4.
You don't have to remember it as long as you know where to find it. You might want to remember, for a test, but it's 9.8, so that's not hard. Electromagnetic is another type of force. Electromagnetic force is a force associated with electric and magnetic fields. If you've ever seen on the movies or anything where the big thing will come out and pick up a car and take it and put it into crusher so they can turn the car into a block of metal, about this big or whatever. That is electromagnetic. Okay? It's a magnet. It's a huge magnet anyhow, but there's a switch that they throw that sends electricity to it, and then it becomes electromagnetic, which makes it a much stronger magnet. Okay, and that way it will pick up a really, really heavy
have a
car.
magnet and then add electricity to it, break it down?
Mhm. You don't always. You can take like a nail and actually wrap it, and it will become. But a nail is magnetic. It's not a magnet, but it is magnetic. Okay. Nuclear forces or forces that holds atoms and their particles together. Tension. Okay. A pulling force that is exerted by a string, cable, or chain on another object. You ever notice how a lot of the physics and chemistry terms are used in our everyday life? There's tension between people. Chemistry, all the lovey-dovey ones, a lot of those comes from chemistry terms and things. All right, elastic. And an elastic force is a force exerted by an object trying to return to its natural length. This is modeled by a spring that has been pulled by an external force. Well, it's pulling back while trying to return to its original length. When we get into, when we talk about elasticity energy, we will, I will show you a couple of videos. One of them is these guys, championship slingshot guy, and he's got all kinds of different slingshots. But when he loads up his ball bearing that he shoots, and he's real quick. He's up, he's stretching it out as he comes up, and he releases pretty much immediately. And the reason being is, if you pull it up and you hold it, it loses energy, and it does not generate as much speed and force behind it.
Because wouldn't it be getting used to the tension of it?
No,
Okay.
son, you have to trust me on this. It loses energy. The longer you hold it back, it loses energy.
That's why
We
when
can
people
prove
like
it.
archers in movies,
Yeah,
they're like,
we can prove it. We can prove it with rubber bands a little later on in another class. We'll prove it with rubber bands. Okay.
do you really want to?
Okay.
Okay.
Well, in a controlled environment, we can shoot rubber bands. All right. Interesting facts about forces. An object that is accelerating in a circular motion experiences centrifugal force. That is where you can take that bucket of water and swing it all the way around, and the water will not spill. Okay, Mr. Feeney, if he still has it, I will borrow it. He's got this really cool thing. He made of plexiglass with 4 pieces of string coming off of each corner, and you hold it. You've got a little handle to it, and you can put a plastic cup with ball bearings, or not ball bearings, marble, something like that in it, and you can get it swinging and go all the way around, and those marbles will stay right in there.
Yeah, I've
As long as I keep a constant speed, the force keeps them in.
I did that.
It's pretty cool.
I did that yesterday with my, or inside with my
Yeah.
candy basket, but I didn't go fast enough and it spilled
Yeah.
everywhere.
All right. Now, torque is a type of force that measures change in rotational speed of an object. Torque is an important feature of an automobile, especially trucks. Remember, I told you about the big guy that I was in the service with that could put on what we refer to as the Jesus nut on the helicopter that held the main rotor blades on. Because if it came off, then you better be right with Jesus because that was your next stop.
Well,
So it was referred to as a Jesus nut. But the torque wrench on that thing, the torque you had to apply to that the nut was unbelievable. I mean, it was thousands of pounds per square inch that had to be applied to the thing. Not too much, not too little, it had to be the exact thing. And the torque wrench was probably 8 feet long, so you could get more leverage to it. And it would take 3 to 4 guys to torque it. And this great big guy could get up there and put it on that nut and stand on the far end and actually torque it by himself.
wait, right in
It was
front of the nut?
It was unbelievable. He was a very, very strong mountain boy from West Virginia.
Like the strongest man.
The 4 fundamental forces are gravity, electromagnetic force, the strong nuclear force, and the weak nuclear force. Okay? All right. Well, I hope you enjoyed it and maybe even learned something.